Hello interwebs, welcome to Let's Fix Computers, or Let's Build Electronics, or whatever title I end up putting on this during editing. We're going to talk about LiPo batteries today. And now, to be more specific, we're going to talk about LiPo cells, lithium polymer cells. Now, during this video, while I'm rambling along, I will doubtlessly use the term battery and cell interchangeably. However, firstly, before we get started, let me just be clear. A battery is comprised of cells. So multiple cells create a battery. So when I say a LiPo cell, I'm referring to just a bare cell. And a LiPo battery would be two or more cells that are wired together somehow. But while I'm waffling, I will probably slip and use them the wrong way around. So please forgive me if I do that the wrong way around. I will try and explain them. I will be explaining a bit more carefully how you wire cells together to create a battery though. So let's get started. So what I'm going to be covering in this video is the different types of LiPo cells, how you can wire them into batteries, when they can be dangerous, what you can do with them, and just generally demystifying them. Because a lot of people, I think, are fairly afraid of LiPo batteries, and there's a lot of fear, uncertainty, and doubt surrounding them, where people go, so, "Oh, that's really dangerous," and "Oh, you don't want to mess around with LiPo batteries," and "Oh, they're a death trap," and things like that. Certainly, in the in some of the hobbyist world, especially if you look at areas like airsoft, a lot of people are terrified of LiPo batteries and still use Nimi batteries for their airsoft guns. And, you know, it's just, they're not that scary. Anyway, let's start by talking about the different sizes and shapes of these things. So what I've got on the bench here is a big variety of different LiPo cells. And I'll go through them all. So firstly, the kind of LiPo batteries that you'll probably encounter quite often would be stuff like this. So these are laptop batteries, and this is the kind of thing that you will commonly encounter as a general user. So this is from a MacBook Pro, and this is from an old HP laptop. And I'll be showing you what's inside both of these things to help you understand that what looks like just a big box with a couple of terminals on it is actually very simple on the inside. So that is the kind of thing you would encounter. Then the two most common types of cells that you will encounter are what I refer to as flat cells, like this one, which, as you can see, is literally just a flat pad, and they come in various dimensions, various thicknesses, but generally speaking it will be some kind of flat rectangle with two tabs, a positive and a negative, sticking out the top. The other common type is the more traditional cylindrical type things. Let's take one out of this torch here, which is a bit more familiar. So this guy, this is known as an 18650 cell. It looks like a big AA cell, and as you can see, it's got 18650 written on it, so hence the name. Again, this is a LiPo cell. It's not a battery, it's a cell, because it has a single cell. A battery would be something like this that has multiple cells in it. So the 18650 is a very common type of cylindrical cell. It's the most common one there is. It's very accessible. Like, as you can see, you can treat it like just a big AA battery. And in this case, it's powering this LED torch here. And because it's LiPo, you can get a pretty decent spotlight out of it. You know, this is allegedly 1,000 lumens, although I've seen it branded under various other brightnesses. But I digress. So those are the cylindrical types. Now, the flat cell types, where's a good example of one? This is a good example of one. This is a teeny tiny little cell. Now, this one, this is labeled 40, 20, 30. Now, on the very small ones like this, that means it's 4 millimeters thick. And let me just grab there's my calipers. So it's 4 millimeters thick, near enough. Then it is 20 millimeters wide, near enough. And it is 30 millimeters long, 30 millimeters. So that's what that number means. And on the thicker cells, so here's a fairly beefy one. This is a 104755. Now, once you get to 10 or more millimeters thick, they up it, so it now becomes 10 millimeters rather than 4.0 millimeters. So this one is 10 mil thick, 47 is 47 mil wide, near enough. and it is 55 mil long. Near enough. So obviously there's a little margin of error here and there, but you know, because of the weird shapes, they don't always come out the perfect size. So this is how you decode the sizes of LiPo cells. And this is how, when you open up a device and you have a LiPo cell in it, and you're like, where would I find a replacement one of those? Or if you want to try and retrofit LiPo to something, by looking for these numbers, by searching for a number that's approximately the kind of size you're looking for, you'll probably find something that's near enough. So, for example, these tiny little cells that I bought here, I bought one of these to put into widgets and to replace a dashcam battery. So that is the size codes. So the next thing to cover is voltages. Now, a standard LiPo cell is 3.7 volts. And this is regardless of the size of the cell. So this tiny little one here, 3.7 volts. This big huge one, still 3.7 volts. The 18650, 3.7 volts. So they're all the same standard voltage output. Now, however, that is 3.7 volts nominal voltage. And what I mean by nominal is that is the average typical voltage it puts out. In reality, the voltage actually varies depending on the amount of charge in the cell. So at minimum charge, you expect to see about 3.2 volts in a LiPo cell. At maximum charge, you will charge them up to just shy of 4.2 volts. So your actual range is about 3.2 to 4.2, but on average, it wants to sit at about 3.4. But on average, it wants to sit at about 3.7 volts. Hence the reason why they're all labeled 3.7 volts. So this makes them very predictable. The capacity of the cell is measured in milliamp hours typically. And so I will use the term milliamp hours or amp hours interchangeably during this. A milliamp hour, there are 1,000 milliamp hours to an amp hour, because a milli is 1,000th. So if we look at these two cells again, as you can see, they're both 3.7 volts. This one is 3,500 milliamp hours. This one is 200 milliamp hours. So that is the difference in the size of them. They both put out the same voltage, but this one, because it's a much bigger cell, is 3.5 amp hours, but this one is 0.2 amp hours. Hence why it's a tiny dinky little cell. It doesn't hold much. So that is the difference in capacity. So in order to put these things to use in a battery, you can combine your cells in different ways to create different amounts. So what I've got here, these batteries here, this is a 3-cell battery. And what that means is we have 3 LiPo cells that are wired in series to add up their voltage. So 3.7 times 3 gives us 11.1 volts. Now, because we're in series, we multiply the voltages, but we keep the same capacity. So each cell is 1,300 milliamp hours, but while they're wired in series, we multiply the voltage up to 11.1. Now, because we've increased the voltage, this means that this battery has much higher current capabilities because the current is being spread across the cells. So on the end of this, we'll see 2 outputs. We've got the main positive and negative terminals that go on each end of the battery. So we've got the negative to cell 1 negative, and we've got the positive to cell 3 positive. And then they're wired in series in the middle. And this is called the balance cable. And from here we have a common negative, and we have 3 wires that come off of the 3 cells in the battery. And this allows a charger to monitor each individual cell in the battery to ensure that they're all in balance with each other, because you don't want one cell to run flat while the others still have lots of charging. So this allows us to balance the battery and ensure that all the cells are evenly charged. And likewise, if we have a look at this guy here, this is a 4-cell battery. So now we've got 14.8. So if you take 14.8 divided by 3.7, you end up with 4 cells. And if we look on the side, you can see 1, 2, 3, 4 cells. And this is a 1,300 milliamp hour battery. So again, you'll notice we actually have the same capacity. So you might say, oh, well, do they hold the same amount of power? And it's like, well, no, actually not. Because this is a 4-cell, it's got a higher voltage. So although they have the same number of milliamp hours, this is a higher watt-hour battery because it's at a higher voltage. So when you're talking about battery capacity, a watt-hour is a far more accurate way of stating the capacity of the battery. But unfortunately, the standard is to use the amp hours. But this gets really squicky when you start working in different voltages, as you can see here, because these guys both say 1300, but this is actually a much bigger battery because it's a 4-cell with a higher voltage. And again, it has much higher current capabilities. The final number that you'll often see is this C rating. So you notice we've got 20C here and we've got 40C here. This is the current capabilities of the battery. So what this means is that this can handle 40 times its capacity in current. So theoretically, you take 1300 times it by 40, and that is the peak current that this thing can draw. So 1300 times 40 equals 52,000. So that is 52 amps that this thing can draw at peak load. So if we actually then times that, times 14.8, so you could actually run 760 watts off of this battery, only at peak. But for a peak, you can actually deliver that amount of power. You could start a car from this thing, as long as you did it quickly. That's how much energy these things can deliver. So as you can see, these capacity ratings are massively higher than any other kind of battery that you may have encountered before. If you tried to do this off of a Niamide battery, you'd blow it up, you'd melt it down. But Lipo has massive burst current capabilities. And likewise, that works for charging as well. You could theoretically charge it at its charging C rating, which may be different from its discharge C rating. So watch out for that. Most of the time, this is the discharge C rating. So that is the numbers on the battery. That's what they mean. So if I pick up 3 of these dinky little cells, so what I can do with these is, if I wire them in parallel, if I join all the positives together and all the negatives together, I end up with 3.7 volts and 600 milliamp hours because we multiply the capacity. If I wire them in series, so we go positive to negative to positive to negative to positive, we multiply the voltage into 11.1, but we keep the capacity. So we'd have 11.1 volts, but still only 200 milliamp hours because we're multiplying the voltage, not the capacity. So that's how you can wire up your cells together to create a battery. And then by wiring them in different combinations, you can create whatever battery you need. So for example, I could take 6 of these guys and we could put 3 of them in parallel for 600 milliamp hours and then put another 3 in parallel and then tie those 2 banks in series to create a 7.4 volt 600 milliamp hour battery, which would be 7.4 from the 2 3.7s and 600 milliamp hours because we've taken 2 sets of 600 and put them in series. And so this is how these are wired up. Now I'll show you examples of these in here because we're likely to find that exact configuration in this battery. Another important factor to consider when looking at LiPo cells is whether it's a protected cell or not. Now, as I mentioned, you don't want a LiPo cell to go outside of its range of approximately 3 volts to 4.2. You don't want it to go too far over and you don't want it to go too far under. So quite often you will find that LiPo cells have a protection circuit. So notice that little circuit board on the end there underneath the yellow Kapton tape. That's a protection circuit. And what that's got is it has 2 chips on it. One of them is a monitoring chip that will monitor the voltage of the cell, and the other is a dual MOSFET package, which allows the control chip to regulate current going in or out of the cell. If it detects that the cell voltage is too low, it won't allow any power to go out of the cell, thus preventing the cell from being overly discharged. And if it detects that the cell voltage is too high, it will prevent any power from going into the cell, so preventing it from being overcharged. So these protection circuits are very helpful in making sure that the cell cannot catastrophically fail, which is part of the safety of a LiPo cell. If you have an unprotected cell, like this one here, notice this just has 2 bare tabs on it. So this cell has no protection on it at all, and is completely dependent on whatever system it's connected to from handling that current and making sure that it cannot be overcharged or discharged. But this one, or also this one that I have, this also has a protection circuit on it. So you can see the 2 tabs there and there go onto a circuit board, and on the other side of that circuit board will be a couple of chips, and then it's got 2 leads coming off of that for the output of the cell. So that is cell protection. So some devices will rely on that cell protection. If a lazy device will just rely on a protected cell to handle its own maximum charge and discharge value. But if you have a good, well-designed system, it will have a proper controller. The laptop batteries usually do this in the battery controller. But as I say, if you're powering a widget, ideally you want to handle a protected cell that cannot over-discharge itself. Alright, let's talk about failure modes. So the most likely failure mode you will see on a LiPo cell is this. Please excuse how grubby this cell is. It's been sitting on the floor next to my bin wanting to be thrown out. But I've got to collect all my dead cells up and take them down to be recycled, because you don't really want to chuck these in the bin. Anyway, so first of all, a lot of the time people see these puffy cells and they immediately panic, and I used to as well. I used to see cells like this and go, ugh, you know, don't want anything to do with that. But the actual reality is these are not nearly as dangerous as they look. So what is happening here is when the cell fails because it's been overly charged or discharged, or it's just gone into some kind of runaway condition, the electrolyte, I think it is, the chemicals inside it, they convert into gas. They convert from a liquid form into a gaseous form, and that causes the cells to puff up like this. And this will do 2 things. Firstly, when the cell puffs up like this, you don't have that compact sandwich holding all the layers of the battery together. They may have widened out slightly, which prevents them from working properly, because you need the cells, you need the film layers in the cell to all be sandwiched together in order for the energy to pass between them and to generate current. So that prevents the cell from being able to build up any useful voltage. The other thing, of course, is that because the chemicals inside it are what actually operate, because it's a chemical storage device, that is what actually makes the device work. With less electrolytes in there, I think it's called electrolytes, obviously that is lowering the capacity of the cell as well. So reduced voltage, reduced capacity means the cell don't work. So the reason why this isn't a particularly dangerous condition is that you might look at this and go, oh, that's in danger of bursting or exploding or something like that. And the answer to that is no, not really. These flat cells, they are incredibly tightly packaged. And when the cells puff up like this, they can reach incredible amounts of internal pressure. These things can puff up with enough force to split battery casings open, laptop cases on. I've got videos of MacBook Pros with bulging batteries where it's shredded screws out of the bottom of the case. You know, so these things can reach incredible pressure without bursting. So trust me, this thing ain't gonna burst. So as you can see, I can manhandle this and it'll be fine. What can make it dangerous, however, is the gas that's in here is toxic. It's nasty stuff. You don't want to breathe it in. You will know if it's venting any of that gas, which it may do. I can smell this one venting now. You will know if it's venting any of that gas because you will smell a very acrid smell. To me, it smells like a sort of a very acidic, sour apple smell. It's very distinctive. You'll know it when you smell it, and if you smell it, then the battery is the cell is leaking. Now you can sometimes bend the rules a bit. This cell I've got over here, this one I've actually the outer layer of it got nicked with a blade when I was taking it out, and that caused it to vent slightly. And I've basically just taped it up with Captain tape to reseal it. And very occasionally I get a very faint whiff off of this cell. I don't drive this cell very hard, but it does still function. It works just fine. I wouldn't recommend using this in any serious project, but if you're just messing about and learning about lipos, don't panic if you catch that whiff. That doesn't necessarily mean that the cell is just immediately dead. Just obviously you can't use that in a production product. You know, if I had a mobile phone battery or a laptop battery that had that smell coming off of it, that battery's got to go. You can't leave that in a working device. That's not a good idea. But if you're just messing about with it, you'll be all right, basically. So that is that. 18650s, I've never seen one of these rupture or bulge at all. The can is just too tough for that. So I don't think that can happen with these. But I stand to be corrected. It might be that someone's managed to see one of these where it's like started leaking out the top maybe or something. I don't know. Never seen that myself, but it's not impossible. What was I going to say next? Oh yeah, so the conditions under which cells are dangerous. Now, there's going to be numerous videos on YouTube that show two things. You're going to see videos where people stab a lipo cell and nothing happens. And they go, you see, they're not dangerous at all. And likewise, there's also going to be videos where people stab a lipo cell and it bursts into flame. Both are true. The clincher is how charged is the cell. Now, what happens when a lipo cell catastrophically fails into a fire like that? It's usually short-circuited. So this can happen because the cell has been damaged. For example, if you pierce it with a knife, the metal knife is going to cut through the film layers of the cell and short them out against each other. This allows current to flow through that short circuit inside the battery. So it's the same as touching the two terminals of the cell together. And because of the sheer volume of energy that a lipo cell can store, I've mentioned before in the video about how, like, you know, this one, fairly beefy lipo cell, this can start a car. You know, once, but still, you know, this will pass 100 amps. The amount of energy that's stored in those, that when it goes into a dead short circuit, you're going to get a lot of heat in a very short amount of time. And when you have a lot of heat very quickly, you have a fire. And when you have a very fast fire, you have an explosion. That is when lipo cells can rupture and catch fire and spit flames and things like that. So it's not that this thing is just going to spontaneously combust into flame. It probably won't, but it can do if it's mistreated to that point. If it's completely flat and has no energy stored in it because it's been discharged down to 0 volts, you could stab it with a knife and nothing will happen because there's no energy in it. There's nothing in there to short out. So that's why some of the videos, they catch fire and sometimes they don't. It depends on how charged it is. And if the battery or the cell that is being stabbed is completely failed, as they often are when they've been removed, because that's why it got removed from the device in the first place, it'll probably be stone flat and not have enough energy to produce any flames. The other condition where you can get flames from these is if you take one of these apart and unravel the film layers between them, some of the coatings on those layers can spontaneously combust. If you have a look at Big Clive's YouTube channel, he's done videos before where he's taken apart an 18650, peeled apart the film layers to show you how it's constructed. Very interesting video. I recommend watching it if you're enjoying this one. And the film layer on one of his cells, after he pulled it apart and exposed it to the air, caught fire. I mean, it smoldered, you know. However, it still spontaneously combusted with no source of ignition and no short circuit. So it is possible and it can be done, but it only happens under very specific circumstances. And those are quite difficult to reach. So anytime you've seen stories of laptops and mobile phones catching fire, it's usually not because the lipo cell spontaneously combusted, but because something else in the device failed, causing a dead short circuit on the cell or internally in the cell. With iPhones, it might be because someone fitted a third-party battery, didn't put all the screws back in, and a screw was left on top of the cell, and when it was all assembled, that screw pressed into the cell and pierced it. That is one such example of how it can happen. Alright, so now there's one more bit of theory learning, and that is how to spot phony LiPo cells. Because you will see this a lot when you're messing around with LiPo cells, is batteries that lie, basically. So let's start with my Tanseran 18650 here. This guy claims to be 3 amp hours, 3000 milliamp hours. Now, for an 18650, that's quite plausible. You can get 18650s. The biggest I've ever seen, I think, is 3.5 amp hours, 3500 milliamp hours. But those are pretty uncommon. Genuine ones of that capacity, you're going to need them to be made by someone like Panasonic, you know, who are expert cell makers. But this one claims to be 3 amp hours, so you would say, wow, that must be a pretty good one then. It's like, no, actually, I've measured the capacity of this one, and it's only 1 amp hour. And this is not an old tired cell either. This has only been cycled a couple of times. It sits in my torch, which is an LED torch, so it doesn't take that much of a beating. But it only clocked in at 1 amp hour. So basically, when they wrote 3000 milliamp hours on it, they lied, basically, because it's a cheap cell. Now, the problem is that because all 18650s look the same, you might say to yourself, well, how the hell am I supposed to know whether a cell is lying or not? Now, with an 18650, the only way to really know is to just measure the output. There are a couple of other giveaways that you can look into, though. Firstly is the weight of the cell. This cell is very lightweight, and compared to this green one, this one is supposed to be 2 amp hours, and it's actually heavier than the Tanseran. So that straight away is a giveaway that this is a phony cell that actually has less material inside it, because the 18650 is just a metal can filled with a spiral wrap of the LiPo layers. And so because this one doesn't weigh much, it's going to have less material in it. And that might be that it's shorter, or it's just not very tightly wound. The point is there's less material in there, therefore it has less capacity. So the weight of the battery is a good indicator for how much might be inside it. That's your first giveaway. Brand is another good one. If it's made by a decent brand, like these purple ones, these are genuine 3 amp hour cells. These are made by LG, so you know they're probably going to be pretty decent. This green one is a Sony cell, so you know when it's in good condition, it's probably going to be legit. And again, if you get a Panasonic cell, a genuine Panasonic cell, not something you bought off of eBay, then it's probably going to be legit. However, some no-name brand like this that says it's 3000 or even 4000 milliamp hours, they're going to be lying. I can almost guarantee it. Now, one of the things that I prefer is if we take the flat LiPo cell ones like these, it's a lot harder to fib with these batteries because they are as big as they need to be. You can see the actual layers that are just wrapped in plastic here. So it's very difficult to lie about the capacity of these because the size of the cell will give you away. So both of these cells here are both 3.5 amp hours. And as you can see, that's legit because this one is slightly smaller in dimensions. They're about the same width, but this one is slightly thinner and slightly shorter, but it's also a fatter cell. So you can see they've got space to put at least another winding or two on that. So it's quite fair to look at those and go, oh yeah, well those are about the same capacity then. And when we figure out the numbers on them, that tallies up. This one is a 13.34 watt hour cell. And if you do the maths on that, which I'll display on screen, that clocks in at approximately 3.5 amp hours. Now, this is an eBay cell that just happens to be a decent one. And this is a genuine Apple cell from an old MacBook Pro battery, a genuine MacBook Pro battery. Now let's bring in a fake cell. So this is a fake cell from a knockoff MacBook Pro battery. This guy claims to be 4 amp hours, 4000 milliamp hours it says on the label, but look at the dimensions of this thing. Actually, let's compare it to the Apple one because it's almost the same dimensions as the Apple cell. It's about the same height, it's it's slightly narrower, and it's nearly half the thickness. Yet this reckons it's 4 amp hours. It's smaller on almost all of its dimensions and noticeably thinner, but yet it claims to be a full half an amp hour bigger than this one. So you can look at this and go, there's no way that's a 4 amp hour cell, because when I compare it to a 3.5 amp hour cell, it just doesn't stack up. There's not physically enough space to put the material in there. You know, the size of the cell doesn't lie. You cannot lie with that. I mean, again, with the 18650s, because it's a metal can, you can tightly wind it really. You can wind it really tightly and cram loads of material in there to make a high capacity cell. But these flat ones, you can't do that with these. The windings on them will be fairly standardized. And the physical size of the cell just cannot lie. Even if you made one of these that was really tightly packed and really vacuum sealed to create a lot of pressure inside that cell, you're only going to gain maybe a millimeter or two. So that might stack up if they're very similar in size, but you know, one's slightly thicker or something like that. But when you get a difference that's as big as that, you know, nearly half the thickness and not as wide, yet claims to be higher capacity, no way. Absolutely not. So that's how you can spot the fake cells with the flat ones. So, and then with the 18650s, you've got to be a bit more critical. You have to decide, is it a reputable supplier? Is it a reputable brand? And does the battery actually weigh anything at all? Because I can swap these around in my hands, and without even putting them on scales, I can feel that this Sony cell is heavier than the Tanzeren, yet the Tanzeren claims to be a higher capacity cell. So that's how you spot your phony cells. Now, personally, in my experience so far, these cells here, this is the only time I've seen a flat cell that doesn't have any kind of plastic packaging around it lying about its capacity. If the cell is packaged like one of the Nokia style cell phone batteries, where it has a plastic box around it, you know, like an old phone battery, where they used to have the plastic box and the 3 flat terminals at the top. Those ones, again, you can lie about it because it's in a plastic box. No one knows what's inside. However, this is the only time I've seen one of these flat, bare cells lying about its capacity. And notice it has this plastic label on it. Whereas these ones, where the capacity is actually printed on the cell with the barcode and the size code and everything, I think these ones will generally be quite truthful about their capacity. Whereas something like this, where it looks like a, you know, a quote-unquote commercial product, I think these are more likely to be phony cells. So if you're trying to buy a cell on eBay and you want to make sure that you get one that's not lying about its capacity, look for one that looks like it has this kind of marking on it. And again, you know, if I get one of the Dinky cells, notice how the Dinky cell, exactly the same deal. It's got the barcode, the size code, and the capacity written on it. I think these are the most likely to be genuine about their capacity. That concludes the first part of this series. Thank you very much for watching. In the next video, we'll be taking apart the HP laptop battery and learning how we can scavenge the cells out of it, test them, and recharge them. So stay tuned for the next part.